All right, so today I want to talk about Sky Quality Index as a tool for communicating the aesthetic or the quality of the night sky. Is this microphone picking up enough? All right. So we use indices for a lot of things. Synthetic indices are common. There's the Dow Jones Industrial. There's the Consumer Price Index. And we have things like the Air Quality Index. If you live in a big city, you might be familiar with that. And these are designed to condense a lot of complex information into something easily discernible by the public or decision makers. In the case of the Consumer Price Index, it's a bundle of goods that are weighted according to what each person would typically buy in a month. We have very complex indices in our world. The Environmental Performance Index is something that are done for governments, federal governments, to understand how sustainable, how green their country is. And there's a lot of factors that go into this. Versus the hurricane scale, Saffir-Simpson hurricane scale, something where you just want to give people a 1, 2, 3, 4, or 5 kind of very sort of visceral gut impression. So what if we could do one of these for a night sky? So Dan and I have been talking about this for years. And we've been working on some numbers, and we think we're going to be ready to roll this out in the next half year or so. I wanted to share this with you and get your impression. So what are the values of an index? Well, I talked about public understanding. An index can capture professional judgment, and there's a lot of professional judgment in any field, but night skies in particular. Those whose job it is, who know the sky well, want to be able to, in an institutional way, sort of communicate their ideas to the public through some sort of numerical index. Indices have been popular for advancing science over the years, and also very useful for restoration. We are, in many cases, asking cities to shield their lights, to spend millions of dollars. Wouldn't it be nice if we could give them some feedback? One of the ways that we could and should provide feedback is some sort of metric. So this metric, this index, may have utility to that. So, Dan and I spending many nights under the stars, I started to say, what is it about this scene that's so inspirational? And we came up with these 4 categories. The absence of anthropogenic sky glow. The ability to fully dark adapt, for not only your pupil to open all the way, but for your rod cells to maximize the sensitivity in your retina. The unimpaired view of the Milky Way, being able to see that backbone of the night stretch not only above, but horizon to horizon, and not just be a thin strip, but sort of that wide band that you can see under a dark sky. And then finally, just the number of stars that you can see. So these 4 factors, almost everything sort of falls into these 4 factors. Now, there's been some good work along the lines towards arriving at an index. The Bortle Dark Sky Scale is one that we often refer to. 2001 by the comet hunter John Bortle. It's a qualitative index. That's its strengths and that's its weakness. These class 1 skies being the most rare, not only absence of light pollution, but very good air quality, and 9 being a fairly standard urban sky, and of course the range in between. But one man's class 3 is different than another woman's class 4. There's some disagreement, and it's not easy to parse the classes. Also, some of the classes are very broad, encompassing a wide range of conditions. Bortle class 4 is fairly wide, for example. Zenith measures. Now, we've been measuring night sky brightness at the zenith for a while. We have these inexpensive sky quality meters. But there's a real weakness in this, and Dan talked about this. But here's an actual picture from Rocky Mountain National Park. This prominent sky glow you see there is Denver, and then Loveland and my hometown, Fort Collins. You can measure 21.9, almost, well, essentially pristine at the zenith. Okay, with our camera. The sky quality meter would read about the same at 21.8. The wide angle sky quality meter would start to pick up that this was a light polluted site at 21.75. But if you look at the entire average sky, it's 21.45. So if we're just looking at this portion, we are missing most of the light tones. So we have this concept of a canary in a coal mine. We want a sensitive bird that perishes at the first symptom of methane gas. Okay, so we want our environmental indicators to be like that. Essentially, the zenith isn't a sensitive environmental indicator. It's a robust one. It's the last one to die. It's like taking a pigeon into the coal mine. So we want to get away from this. So Dan has this idea of capturing the curve of nature. And what do we mean by this? But you want the curve to be steepest, to render the most information where there's the most detail. We want to emphasize those delicate features that are easily obliterated by light. The faint filigree in the Milky Way, those bright knots on those dark lanes. We want to mirror the physiology of the human eye. We've already talked a lot about the physiology of the human eye and other species, but this is just a human aesthetic index we're talking about here. And there's some interesting analogies to image processing. For example, here's a picture of a couple of galaxies, M81 and M82. That same image with a different stretch will reveal a lot more detail and interest. Same image, just a different gamma curve applied. So what we're essentially doing is doing that with the entire night sky. The National Park Service has all this great photometric data. We have this fancy camera system. We've taken it out on literally hundreds of nights, I think 650 nights of successful data. And here's these images. This is the raw monochromatic image in a fisheye type view and all the locations. And this forms the basis for our sky quality index. And this is the data that we played with. So our index is designed to capture the human aesthetic only. We rate it on a 100 to 0 scale, where 100 is perfect. We measure the entire sky, not just the zenith, and the whole sky is equally weighted. It's a repeatable. As Dan talked about with the natural light subtraction, we want to remove the natural light and just isolate that anthropogenic light in order to get a most accurate reading. And we'd like our index to be equal interval. So we're trying to apply an equal interval quantitative index to an aesthetic factor. This is briefly about the natural sky subtraction. You see that we have these 4 components of the natural sky that we can model. Airglow, which is the broad chemoluminescence of the upper atmosphere. Atmospheric diffuse light, which is just that scattering of light along the horizon. It's a fairly minor factor. The Milky Way, and the Zodiacal light, which is actually fairly bright, but it's so broad and smooth that it's not as detectable to our human eye. So putting all these together, we can model the natural sky, and then we can compare it to the observed, the difference being the anthropogenic. So our camera system takes 36 million pixels of the entire sky. That was too much to work with, so we came up with this grid of a little bit more than 5,000, and these are sort of equal area points. And we take all the brightness factors that are all in all these little grid points, and we put them in these bins. So here's an example of a dark site, moderately light polluted site, and a bright site. And each of these bins are half magnitude intervals. Okay, so this is the dark bin, our category, and it gets progressively brighter into sort of an urban sky will have a lot in the urban category. So the first thing is you just see this histogram move to the right and sort of spread out as one simple statistic of a bright sky. So we then take these bins, which again are down here at the bottom, and we apply 4 factors to these bins. So these are the 4 curves that we developed for our elements of a human aesthetic dark sky. Naturalness. What do we define as naturalness? Basically the ratio of light pollution to a natural sky. If there's more light pollution in that particular spot in the sky than the brightness of the natural sky, we give it a 0. Okay, so that's a very harsh test, but it's what we feel is an accurate test. Again, capturing our professional judgment. The second is the visibility of the Milky Way. Oh, so by the way, the naturalness curve is this red one. The blue curve here is the Milky Way. The number of visible stars is this long snaking S curve of yellow. And then finally, as you get brighter, once you get to about 19th magnitude, scotopic inhibition kicks in. So you start losing sensitivity in your rod cells in your eye. Let's go through these. First of all, so these two here are factors of a lightscape, whereas these two here are factors of the celestial sky. And we thought it was important to capture both aspects, not only for the stargazer in us, but also just going out and enjoying a natural night, where we're primarily vertical, not lying on our back, and observing the horizon, as we say, walk through a national park at night. So each of these four factors are equally weighted. We saw no reason to give one more weight than the other. So the first one, the availability of a pristine sky, is given a weight of 25%. So what would the score be? So we're doing this out of 100, so each one gets 25 points. So Morristown, this is a bright site in New Jersey, has no portion of the sky that's natural. It's 0. Here's a moderately bright site, Bandelier National Monument outside of Santa Fe. It only gets 0.2 out of 25. So in other words, there's really just like a thumbprint of sky that is dark. So it gets very few points on this factor. Big Bend gets basically 23 out of 25. So that's our harshest test. Our second test is the Milky Way Detail. And to basically build that S curve, we took our model of the Milky Way, which is very accurate, and we added light and basically reduced the contrast, and then figured out what area of the Milky Way is showing at different contrast intervals. So using that function, our bright site gets 1.3 out of 25. In other words, you can only see just 1.3 out of 25 points of Milky Way, if you want to think of it that way. Our moderate site, where the Milky Way certainly spans the sky but doesn't go to the horizon, gets 8.3. And Big Bend gets 24 out of 25. Pretty good score there. The number of visible stars. This is we think we can improve upon this, but this is a fairly rudimentary way of analyzing it at the moment. Bright site 10, Bandelier 20, Big Bend basically 25 out of 25. So you're starting to see that the brighter sites are doing well in this particular parameter, because you can still see a fair number of skies because you've got, some decent skies at the zenith. And then finally, the impact upon scotopic vision. Here, 10 points out of 25. Bandelier gets 21 out of 25. The only places that are really impacting scotopic vision are the core of these light domes, and then Big Bend. Now, there's another little tweak we did here, and that is if you only have 1% of the sky that can affect your scotopic vision, and let's say it's Dan Dorisco sitting there, he's my bright object. Well, the problem is I see Dan out of the side of my eye even if I'm looking this way. And even if I'm looking this way. So even though a small portion of the sky is bright, it affects quite a lot of my experience. So we scratched our heads about this and said, well, what if we do a log function? And that actually worked. So that's what we're using. All the rest are linear, but this particular parameter, we treat it as a logarithm. Okay, you can dim now. All right, so we managed to boil this down into basically a simple spreadsheet here. Simple. It's actually not that bad. The idea is you take your sky measures with whatever instrument that you're using that measures the entire sky. We do this with 5,000 samples. We believe you could do it with as few as like 30 samples of the sky. You just take a measurement here, here, here in a systematic way, plug in the numbers, and you can get this spreadsheet to talk back to you and tell you what the index is. Another issue is spectrum. Right now, this is basically built around the Johnson V, which is midway between the photopic and the scotopic responses. We think that's appropriate for humans. One of the if we were to do one of these for, say, sea turtles, we would be wanting to use a different spectrum. So it's possible to create indices like this for things other than human vision. Terrain blocking is an issue. This is the same site 100 yards apart. The only difference is here we're on top of this hill, and here we're down kind of in just a swale. And you can see that the trees obscure the brightest light dome. So you're going to get fairly different numbers in these two. So we need to have some way to compensate when you can't see the entire horizon. And whenever you're taking measurements at night, you need to think about the changes in atmospherics, not only the scattering due to haze, but also airglow. These same spot a few nights apart, there's no change in the brightness of the town, International Falls. The only difference is that the airglow and the moisture is much greater in this image. So you still have the issue of all that natural variability to deal with. So in my last 5 minutes here, I'm just going to walk through some of the sites that we have. Mauna Kea, pretty much the gold standard. Bortle Class 1. Here's some other parameters. Notice that the brightest is still 10 skies because we're getting, in this false climate range, just a little bit of these cores here. But this gets a 99. That's what the bin looks like. So almost all the points, those 5,000 points, are in the darkest sky. Capulene Volcano, turn that into false color. That's the anthropogenic only. And then here's what the bins look like here, and that gets a score of 92. Acadia, one of the best spots on the East Coast, but fairly light polluted, as you can see. Bortle Class 3, to tell you where we are. There's the anthropogenic only, gets a score of 86. Rocky Mountain, I showed this picture earlier. There's our false color. There's our anthropogenic only. And you're starting to see this smearing out of the statistical bins. It's 76. So in our professional opinion, based on this photometric results, 3/4 of the grandeur, the inspiration, the aesthetics of the sky are present here, with 1/4 diminished. Notice that the sky quality meter is giving a very optimistic 21.8. 22 is like perfect. So again, the zenith is not telling not even part of the story. Glen Canyon, so here we are in a national park, but tucked up against Page. There's the false color, the anthropogenic. We give this site a 62. Padre Island, turtle nesting area. Bortle Class 5. There's our false color, our anthropogenic. Notice that when we do the anthropogenic subtraction, it's making less and less of a difference as it gets brighter. No dark here. And we give that a 40. Santa Monica Mountains. So this is where people in LA go to stargaze. Griffith Observatory is actually a little bit brighter than this. We give it a Bortle Class 7, but a sky quality index of 28. So there's our false color. Very little change when we did the anthropogenic isolation. There's our histogram. So now we're at a point where about 1/4 of the grandeur of the sky is available. And our current poster child for the darkest park, this is Rock Creek Park. It's an NPS unit in Washington, D.C. Same color ramp on each of these, so you can see it's fairly bright. This is what our histogram bin looks like, all of it sort of concentrated into some very bright bands. And we give it a 10, and those 10 points are based on, there's a few stars you can see, and also your scotopic vision isn't completely blown by our estimation. So there's a little bit of dark adaptation there.
When was that measurement taken?
Last October, so 13 months ago.
They are converting a lot of sodium to LED, so your scotopic is probably shot to hell by now.
We'll go back. Things change. All right, so to wrap up here, we think that in addition to this being a tool for the National Park Service, that other instruments can do this. Probably a simple fisheye camera design can make this work. And we want to make the spreadsheet available eventually for everyone, and also have the natural sky subtraction embedded in it. We do need to figure out some compensation issues, like when you can't see the entire sky. Wanted to just emphasize that this is a human aesthetic index. It would be interesting to develop other indices like ecological ones, or one that's based more on, say, an urban or cultural experience. It certainly has some utility for international dark sky parks and reserves, and being able to track and also to rate each of these. I think the public and the media is constantly asking me, like, how good is it? Can you give this sky a grade? Is it a B+ sky? Is it an A- sky? I think this index goes a long ways towards that. And Dan and I still have some more work to do on this, but it's going pretty good so far. So that's it.